We have arrived at page 6 of our final review worksheet. In this segment, we're going to be working problems dealing with indefinite integrals. This is the reverse differentiation process. So if you've done your homework and you've learned your derivatives, we're simply applying those in reverse. So problem 20, we're looking for the indefinite integral of 12x squared minus 3x plus 3 with respect to x. So we're going to apply the reverse power rule on each term. So let's work through this one carefully. To integrate that first term, 12x squared, like we do with derivatives, we'll filter that constant multiple through to the antiderivative. Then we apply an opposite process. We're going to add 1 to the exponent and divide by that number. Remember, when you're differentiating, you bring the original exponent down in front to multiply by it, and then you decrease the exponent by 1. When you're integrating, you're doing the two opposite processes. You're increasing the exponent, and you're dividing by that number. For the next term, we have negative 3, which comes through to the antiderivative. And then we are going to increase the exponent on that x by 1 and divide by that number. And the last term, we're integrating 3. Notice you could view that as 3 times x to the 0th power. So if I add 1 to 0, I get 3x. Okay? And again, practice checking your work by differentiating. If I differentiate 3x, its derivative is 3. So I'm just going in the opposite direction. Now, anytime I integrate, I have to consider the possibility that there's some sort of arbitrary constant out here, because the derivative of any constant is 0. So I could have a little 0 over here, which represents the derivative of that constant. So every time you integrate, make sure you include that arbitrary constant. Let's go ahead and simplify here and express our antiderivative. We end up with 4x cubed minus 3 halves x squared plus 3x plus c. Don't forget that plus c, it's worth a point. Problem 21, we're going to rewrite the integrand before we apply the integration process. Now, since I'm not integrating, this is a pending operation, I'm going to carry that integral sign to this next step. Then I'm going to distribute the 8x to end up with 8x to the 5th plus 48x, and I'm integrating with respect to the variable x. Okay, so all I did there was rewrite the integrand. Now I can go back and integrate term by term. So when we integrate, we drop this operator. That means I'm executing that operation. So let's carry our constant multiplier through to the antiderivative, and let's apply our reverse power rule to x to the 5th. I'm going to add 1 to the exponent and divide by the same thing. Same process for the second term. I've got my coefficient 48. Then I'm going to add 1 to the exponent and divide by that same thing. Again, don't forget your plus c. Remember, this antiderivative, if I differentiate it, should give me the original integrand. So when I differentiate a constant, I always get 0. So there's potential of having that constant in every antiderivative. Let's reduce. 8 and 6 have a common factor of 2. 2 goes into 8 4 times, into 6 3 times. These also have a common factor of 2. So our result ends up being 4/3 x to the 6th plus 24 x squared plus c. Looking good. On problem 22, notice the power of x is located in the denominator. I'm going to rewrite it just as I would as if I wanted to differentiate it. I need to express it as a power of x so I can apply my reverse power rule. Be very careful here though. The coefficient 1/10 stays the same. That power 5 only applies to the x. So when I get it out of the denominator and give it that negative exponent, it again only applies to the x. The 1 and the 10 stay where they are. Now we're ready to integrate. So we keep our constant where it is. we're going to add 1 to the exponent, right? Now when we add 1 to negative 5, we get negative 4, and then we divide by that same constant and tack on our arbitrary constant of integration. Now I'm going to attempt to express the result in the same form as the original integrand. I notice it did not use a negative exponent, it was in fraction form. So I'm going to rewrite this in fraction form. Okay, so let's multiply our two constants together. 10 times negative 4, those are both in the denominator. It's a negative 40. Leave a 1 there in the numerator. And then we'll take our x to the negative 4th, move it to the denominator, and change the sign of that exponent. So our antiderivative is negative 1 over 40x to the 4th plus c. Again, if you're comfortable with your differentiation rules, integration is not too difficult. You just got to get your mind straight on changing a few details. Until we get to the substitution process. If you had trouble with integration by substitution, let me tell you that is normal. This is a difficult process. It takes a while to get used to. So please let me give you some tips here. Number 23, I need to find the antiderivative for. I cannot simply apply the power rule term by term because I'm dealing with the quotient of two functions. Now, I don't have a reverse quotient rule, but I have a process called substitution. Notice in the denominator, I have the composition of two functions. I have a function raised to a power. Now, if I were differentiating something like that, I know it would require the chain rule, right? If I have a composition and an integral, I'm going to use substitution. Okay, so what we're going to do is choose the substitution u to be the inside of this composition. Okay, so just the base. So I know that I can rewrite that denominator as u to the 9th. It's going to simplify very nicely, okay? However, I still have some junk left over in the numerator of the integral. So what I'm going to do is differentiate both sides of my substitution statement. But I'm going to use different notation. The derivative of u is 1, we know that, but I'm going to express it as du. Okay, the left side of your substitution statement will always be du. On the right side, I'm going to differentiate like normal, but I'm going to tack on a dx right here. Now, what I've done is simply separated our ordinary derivative notation into two sides, right? If I think of multiplying both sides by dx, I would end up with this statement. Okay, now what I want to do is see if I can spot this dx term and its details as leftovers in the integral. So let's rewrite our integral in terms of u. Obviously, in that denominator, we have u to the 9th. But I still have this 2x plus 3 dx left. I'm going to write all of that in terms of u. It's not quite the same as my leftovers here unless I recognize I can factor out a GCF. All right, so take out a 5. That leaves behind the familiar 2x plus 3 dx. This 2x plus 3 dx lives right here. Okay, so I'm going to replace that by a multiple of du. I want to make this side of my substitution statement look exactly like the leftovers in the integral. I can accomplish that by dividing both sides by 5. So du over 5 is 2x plus 3 dx. Okay? So I can rewrite that 2x plus 3 dx from the original integral now as du over 5. All right, this is kind of a mess. Let's clean it up a little bit. That du over 5 is 1/5 du. I'm going to take the 1/5 in front of the integral. That leaves me with du over u to the 9th. Okay, now to integrate, I need u to be expressed not in fraction form, but in exponent form. So let's call this u to the negative 9th du. All I'm doing here is recognizing the form of the original integral. It looks complicated, but it matches this expression in u. Integrating with the power rule, we add 1 to the exponent and divide by that number, and then apply our arbitrary constant of integration. Okay, let's take that u to the negative 8 back into the denominator and multiply the 5 and the negative 8. We're going to have 1 over negative 40 u to the 8th plus c. Now, the only thing that I have to change here is the u. I need to go back to my original variable. I'm simply going to replace that u with its expression in x. So the antiderivative is 1 over negative 40 times u, which is 5x squared plus 15x to the 8th, plus c. You can check that by differentiation. The derivative should match your original integrand. All right, let's practice another one. The next one, we're going to have to recognize one of our derivative formulas. Number 24, notice it is a quotient, so I'm not going to be able to integrate term by term with the power rule. Instead, I'm going to have to make a substitution just like I did on number 23. The point of a substitution is to recognize the overall structure of your integrand. If you have a fraction, a good choice is to let u be the denominator. Remember, as soon as you make your choice for u, differentiate both sides of this equation. Left side will always be du. On the right side, we get 8x dx. Now this one's a little easier. The denominator is going to be rewritten as u. And notice my leftovers, 8x dx, match this exactly. So that part will be replaced with the u. It's almost like we're making two substitutions here. So our new integral in terms of u is du over u. Now if you don't like it like this, think of it as 1 over u du. I cannot apply the power rule to this. If I rewrite 1 over u as u to the negative 1, and then I apply the power rule, I'm going to end up with a 0 in the denominator. So I'm sort of at an impasse unless I have done my homework and I know that 1 over something is the derivative of what? A natural log function. So the antiderivative of 1 over u is natural log of the absolute value of u. The absolute values there, just make sure that the u is positive to satisfy the domain of the natural log. Okay? Again, check this going backwards. If I were to differentiate natural log of u, I would end up with 1 over u. To finish the problem, I'm going to replace the u with its original substitution statement here, and we end up with natural log absolute value of 5 plus 4x squared plus c. All right, keep practicing those indefinite integrals. In the next video, we will finish our review with definite integrals.